All right, let's talk about a problem that trips up a ton of people in data analysis. What do you do when your data, well, when it has holes in it? Because trust me, if you're not careful, these gaps can lead to some seriously misleading conclusions. So let's dive in and figure out how to handle this the right way. Think about it like this. You're a detective at a crime scene, right? But some of the clues are just gone. Or maybe they're smudged. That's exactly what we're dealing with here. So what happens when your data set has these kinds of holes? I mean, how are you supposed to solve the case when you don't have all the evidence? Okay, so here's the game plan. First, we're going to figure out where this missing data even comes from. Then, we'll put a name to the two main culprits here, censoring and truncation. After that, we'll see why our usual go-to models totally fail at this. But don't worry, I'll introduce you to the specialist, the Tobit model that can handle it. We'll even learn how to interpret its results, and then we'll wrap it all up with a little quiz to test what you've learned. So, let's get right into it. The heart of the issue is what we call limited data. This happens when the thing you're trying to predict, your dependent variable, can't actually take on its full range of values. It kind of hits a wall or maybe a floor, and that's where all the trouble starts. And you know what? This stuff is everywhere. Seriously, think about it. If you survey families on how much they spent on a new car last year, what are a ton of them going to say? Zero, right? Or if you're studying the hours women work, a lot of them will report 0 hours because they're not in the paid labor force. See, these zeros aren't just zeros. They're a hard limit, a boundary in our data that we have to deal with. So this brings us to the two big ways our data can be limited. And it's really, really important to know the difference because they each need a totally different solution. Let's meet our two culprits, censoring and truncation. All right, first up we have censoring. The best way to think about this is like taking a picture in a really dark room. The flash lights up everything close to you, but you can't really make out what's in the deep dark corners. You know the corners exist, you just can't see the details. That's censored data. We have information for everyone in our study, but for some people the value we're interested in is just piled up at a limit, like 0. So we know the person is in our survey, but we only see their hours as 0, even if their true underlying desire to work is something less than that. Now, truncation is a whole different beast. This is like taking that same photo and just cropping the dark corners right out. You don't even know they were ever there. With truncated data, if that outcome variable falls outside a certain range, we lose the entire observation. The person, all their info, just gone from our dataset. We have nothing on them. Okay, this picture makes it super clear. Look at the left side, that's censoring. See that big pileup of dots at the limit? We still have all those observations, we just can't see their true value. Now look at the right side. That's truncation. Everything below the line is just gone, vanished, poof. No dots, no information, nothing. And that's the absolute key difference. With censoring, you've got some information. With truncation, it's a complete blackout for those data points.
So at this point, you might be thinking, okay, can't I just run a normal regression on this and just call it a day?
Well, let's talk about what happens when you try to use the wrong tool for the job. It's not pretty. So here's the bottom line. And you really need to hear this. If you just throw a standard model at this, like ordinary least squares or OLS, your results are going to be wrong. And I don't mean a little bit wrong. I mean fundamentally biased and inconsistent. Your estimates will be systematically off. And get this, even collecting more and more data won't fix it. You're just going to end up believing something that isn't true. And here's what it looks like in practice. This table shows what happens when you run a standard OLS regression on our hours worked data. The numbers you see here? They're basically garbage. Why? Because a model like OLS makes a core assumption that the errors, the mistakes it makes, are random and they average out to 0. But when you have a giant pile of data points stuck at 0, that assumption gets completely shattered. The model just wasn't built for this. But don't despair. There is a hero in our story. When you have a really specific problem like this, you need a specialized tool. And for us, that tool is the Tobit model. The Tobit model, which gets its name from the economist James Tobin, is purpose-built for handling censored data. It's actually a really elegant solution that looks at the problem in a totally different way. So what makes the Tobit model so smart? Well, it splits the problem into two separate questions. First, it asks a simple yes or no question. Is this person at the limit, say 0 hours, or are they working a positive number of hours? It actually models the probability of that. Then, for only the people who are working positive hours, it asks a second question. Okay, how many hours are they working? And for that part, it can use something like a standard regression. It's this two-step process that's so brilliant and what lets us get an accurate answer.
And just so we're all on the same page, while we're really focusing on the Tobit model for our censored data problem, there's also a special tool for our other culprit. If your data is truncated, you'd want to use a truncated regression model. Different problems, different specialist tools. Makes sense, right? All right, so you've done the hard work, you've run the right model. Now comes the most important part. What does it all mean? Let's figure out how to actually read the results and understand what they're telling us.
So we're going back to our example on the hours worked by 753 married women, and you can see right in the output here, it tells us that 325 of them are left censored at 0 hours. This is the classic kind of problem that the Tobit model was born to solve.
Okay, let's just zoom in on one variable here, age. The coefficient is about -59. Now hold on, this doesn't simply mean that for every year older, a woman works 59 fewer hours. It's a bit more nuanced. In a Tobit model, this number is really telling us about the effect on the underlying desire or potential to work. And look at that p-value right next to it, it's basically 0, way, way smaller than our usual cutoff of 0.05. That tells us this is a statistically significant finding, so we can be pretty confident that in this data set, as age goes up, the latent desire to work goes down.
But here's where it gets a little tricky with a Tobit model, and it's super important to remember. A change in a variable like age actually has two separate effects. It affects the number of hours worked for women who are already working, and it affects the probability that a woman works at all. You know, the chance that she has a value above 0 in the first place. Two effects from one number.
Okay, let's pull all these threads together and see just how big of a deal it is to use the right model. This is where it all clicks into place.
Okay, this slide right here, this is the aha moment. Just look at the coefficient for age across the 3 different models. Our standard, but totally wrong OLS model says the effect is around -32. But the correct model, the Tobit, says the effect is almost double that, at -59. And the truncated model, which just throws out all the zeros, gives us yet another different answer. You see, this is why this matters so much. Your entire conclusion about how much age affects work can be wildly different depending on whether you use the right tool.
So let's just recap the big difference one last time. With censoring, you still have all your people, you have all their info, but for some of them, the true value is just hiding behind a limit. With truncation, on the other hand, the people are just gone. They're not in your data set at all, creating a massive blind spot. All right, that brings us to a final little challenge for you to chew on. Imagine a researcher is studying academic performance. But here's the catch. Their dataset only has students with a GPA of 2.5 or higher. Anyone below that isn't just listed as having a 2.5, they are completely, totally missing from the data file. So my question to you is this data censored or is it truncated? Think about it, because getting the answer right is the first step to doing the analysis correctly. Thanks for tuning in.